This month, we're going to hear from our Spinterns, space placements in industry interns, who are currently halfway through their 8-week internships. We'll hear what they've been up to so far in each of their projects and what progress they've each made. First up, we have James and his project, Open Source Satellite Ground Station Development.
So, my spinternship has been about building on the work that has already been done on open source ground station components. So, these are the bits that sit on the Earth. So they're the kind of the Earth side of the gear, and we use them to talk to satellites in orbit, send them telecommands, and receive data back from them, both the payloads and just general data for the satellite. So I'll get started. So my objectives for this project, I was supposed to architect a small scale ground station which can run on something like a Raspberry Pi. So cheap and cheerful hardware which kind of a university or school or university society, something like that, can easily get their hands on. Because I imagine there's going to be a lot of university and school involvement with OSAT projects in the future. So I'm also going to build a working demo of a ground station. So that's kind of the whole computer tracking system, with a rotator as well. So there will actually be something which is capable of pointing at satellites, and their ASEL stands for azimuth and elevation, which are the kind of the 2 degrees of freedom of that you need to be able to track things across the sky. So at the bottom, we have this satellite, which is moving in the satellite dish, which is moving in the azimuth direction, and then this giant ESA satellite, which is moving in the elevation position. And then you also sometimes get these spooky domes, but those just have satellite dishes inside them, and then you can't see where they're pointing. So, and those are mostly used for kind of more professional and military installations. And then I was also meant to produce some instructions and documentation so everyone can repeat my work, and what I've done doesn't get lost, essentially. In addition to this, kind of an extra goal was implement a SDR-based modem, and I'll be explaining what all of those words mean in the next few slides. So on to some of the research which I've done for this. I think it's been about a week and a half doing purely research, and then there's been quite a bit going on as I've understood the brief and the project better and planned out what I'm going to do. So orbits and TLEs. So when you put stuff into space, it tends to move, which can be quite hard if you want to communicate with it. There's definitely some challenges there. So it means the whatever ground apparatus you have with the antennas is going to need to move and follow the device and follow the spacecraft. And one of the ways we do this is with TLEs. So essentially what this component of the project is making a tracking, telemetry, and control system. So and you need to know where a spacecraft is in order to communicate with it. So you're going to have to be doing some calculations, have some software tracking where that spacecraft is meant to be, so you know when you can communicate with it, when it's kind of above you and when it's not. It's not the case with all satellites. Some you'll have in a nice geostationary orbit, like kind of the satellite dishes you'd have for Sky TV and stuff. Those are pointing at a single satellite, which stays exactly where it is. But basically all small sats and CubeSats are in kind of a low and medium Earth orbit, so they're moving pretty quickly. So tracking those objects, a lot of work was done by a lot of very clever mathematicians on formulating methods for tracking these objects around space. And there's a lot of different forces which you might want to take into account, and a lot which you can leave out on for kind of simpler tracking, simpler orbits. And we don't actually need all that much information when we just want to be able to point at something in the sky with a rough degree of accuracy. So, at least from the ground station side, orbits are tracked using TLEs, which are kind of an expression, a compressed expression of the forces acting on the spacecraft and some position and timing information, which will then give us, which will allow us to calculate its current position given the time. It was designed for use on punch cards, so the 2-line element, the 2 lines are 2 punch card lines, and it's been used ever since. Really, there are some better things now, which are used more on kind of for like attitude control and very particular orbit calculations, as well as maybe some interplanetary stuff. But generally, for satellites going around Earth in most orbits, TLEs are absolutely fine. So they're still good enough, at least for what I needed. So I didn't need to stretch that one too far, and it was quite interesting stuff to learn about. The second thing that you have to consider when you're trying to communicate with something in orbit is Doppler shift. So Doppler shift is kind of a phenomenon where things moving relative to you when they're emitting waves is going to compress when it's moving towards you and kind of rarefact going out the back. So with this, like a police car makes a siren. When it's moving towards you quite fast, it sounds much more high pitched, and when it's moving away from you, the pitch decreases. Those are longitudinal waves. Same applies to transverse waves. You essentially get a shift in frequency, and it's used in vehicle sirens as it helps kind of drivers know and pedestrians know where they are, know that they're there, and then help make decisions if they can't necessarily see them. So spacecraft move pretty quickly, often a couple of 1,000 kilometers per hour. So you get quite a lot of Doppler shift, and you need to be ready to handle that on the ground station side. Yeah, just some planes flying over, but it can all be calculated using the TLEs we discussed earlier. So you can have software adjustments for these frequency distortions that you get as a spacecraft passes over where you are on Earth. So my activities in progress on this, I've completed my definition and architecture of my problem and set out what I want to achieve in this internship. I've also completed the GNU radio modem, which is the part of the project which is designed for kind of encoding and decoding data from a satellite, which is actually quite a complex process, and that was moved up to for kind of support work with KernoSat as well, which was both very good for me to test my software and software radio against, as well as it was good for kind of the testing and verification of KernoSat itself. So that was definitely a good part of the internship, helping on that. YAMS is a mission control software which we want to use for KernoSat, and I know a lot of the development team are looking into. It's a very, very nice, very modern software that can be used for kind of dispatching commands to satellites and receiving data from them. And I do have more on that later. So onto architecture of kind of my solution. So this is kind of the high level diagram I drew fairly early on in my project, and this basically defines the whole thing as a system and what the relationships I need to consider in software and hardware. So the large rectangle here, that's going to be a Raspberry Pi or some education grade hardware, but everything inside it is software, and everything outside is hardware. So inside we have the mission control software running. So you want to tell Kernosat or some other satellite to do a barrel roll, that can be done. Or you want to get some data of its current orbit, battery health, solar power, that's fine. And in order to facilitate that connection, because those are just kind of network links that YAMS has between these two. So the modem is the bridge between radio waves. Well, the modem and the SDR together are the bridge between kind of radio waves, what's actually coming out of your dish, and what's happening in software. So the antenna, which in this case would probably be some kind of parabolic dish, is pointing at your satellite. That data is going to the SDR, which can then be processed on the computer to decode the data coming down from the satellite. And that's one of the main parts which I wanted to get done in this project, which I have more detail on later. One of the other key parts of the project is, of course, making sure you're able to know where the satellites are. So when you're actually trying to talk to it, as I kind of discussed earlier, you want the things which have you want to get some data from TLE sources. So use the TLEs to calculate where it's going to be in the sky at the current time, and then you can tell your rotator to move your parabolic dish to the correct position. So in here as well, that's calculating the Doppler shift that we need to accommodate for, which is going to the modem, as it needs to know. And we also have some signal reception metadata feeding back into it. So we might need to potentially adjust or update things on the fly. Yeah, so that's kind of the high level overview. And to dig into the detail, so SDR, that is a software defined radio, and they are really nice bits of kit. The way we kind of modulate and encode data that goes through space is often governed by what the Consultative Committee on Space Data Systems says about it. And they've been publishing a whole lot of stuff since about the 70s on what kinds of things work well when you're trying to communicate in space and what don't. And it's a very useful standard to be compliant to, because there are a lot of ground stations around the world which support CCS DS protocols, and then you can just tell them, you can basically just give them some basic information about your satellite, and you'll be able to get data back from all over the world. So it means you don't need to like co-locate equipment anywhere. So that's one of the main reasons why it's quite useful. It is a fairly dated technology, and a lot of it does actually like predate the internet and various bits. But it's good enough, especially for telemetry and telecommand. So kind of your fundamental satellite operations. So, and this kind of is my journey through as I was trying to learn about what to do for my modem. So I was researching SDR concepts and tutorials. It's quite hard stuff to get to grips with, but eventually stuff starts to sort of make sense, and you can construct a really, really nice prototypes using that software. It's kind of like Scratch for RF engineers, which you'll see one of the flow graphs on the next slide, so you could be the judge. But and I spent quite a bit of time looking for existing solutions, because I didn't really want to reinvent the wheel here, especially when it's so hard to design from scratch. But on every paper on the internet I found about people trying to use SDRs to implement ground stations, they had always left the kind of modulation which is the one used by a large amount of satellites and Kernosat, as it happens. They'd always leave it as a footnote, so it's called OQPSK, and no one had really implemented it. We kind of searched far and wide, and I know Sophie and Sandra were looking for some things on that as well. And then I was kind of learning about it and why it's so difficult to do. It was mostly difficult because people hadn't really done it. they'd mostly done it kind of for the sake of papers and things where you just want to go into kind of some surface detail and a proof of concept, but it was always one step further because it's a protocol that's used a lot more in practice than the simpler ones which are used to model it in theory. And then I did happen to find some really good information on a guy who does a lot of RF for space. He had a blog post about where he was tracking the Artemis Orion capsule, which was one of the NASA missions, I think, at least within the last year. And he was trying to decode all the data from that, and he came up with some good ideas for how to demodulate OQPSK, which I based my implementation on. So, and I use those examples and the information he provided to make a demodulator, which would take like RF data from the satellite and spit out telemetry frames, which can then be put into YAMS. And that made me look very smart. That was quite a good moment when it all got working, but it is mostly thanks to Daniel Estevez for his work on that. And yeah, so I thought I'd explain what a modem is and why I've crossed out the mo. So modem stands for modulate, demodulate. So, and the part of this I implemented was the demodulation. So that's why I've taken out the mo of this bit. Because also it's not particularly responsible to just put it out on the internet and tell everyone how to telecommand satellites. But I'm sure people who really know what they're doing, doing things they're meant to be doing, can figure that bit out. But it was quite nice to figure out the demodulator part. So demodulating decodes data from a channel. So a channel can be anything. It can be like a audio channel. So back in I don't really know, maybe Kevin, I don't know if you remember these. The phone.
Thanks. Yes, I do.
You put handheld phones on this thing which connects to your computer, and then that will go and connect you to a dial-up server. So basically, it just makes noises over the phone line, and it uses that to transmit data from one place in the world to another. It's not very fast, but it got the job done. And then here in the middle, there's like the more modulating encodes data into a channel. In the middle, that's a fairly common satellite modem. So that's what you'd like traditionally put in a rack somewhere with like Goonhilly ground station, and that's going from our like radio frequency into packets of data. And then one that people are probably more familiar with in your homes, if you have Virgin Media or any other provider, you'll have something that connects you to the kind of the wide area network, and that has so in Virgin Media's case, that's like a cable modem. So they'll have a piece of coaxial cable which comes to your house. In a lot of places, it's fiber. It's still the same. It's a fiber modem. Or just a copper twisted pair cable modem as well. Very common. There's often some terminology confusion because those include kind of routers and access points in the same box as well. But because it's much easier to have one thing to cover your whole house than several different boxes, which definitely used to be the norm. Right, so CCSDS provides a set of standard techniques to use for modulating data through space, and I had a look at quite some of those, and they are very interesting, and a lot of them are very old, but as I say, they still work, and you can actually get fairly reasonable bandwidth, at least for anything that you'd need from a satellite through them. So unless there's some very big reason not to use them, people tend to use them. So When you have a signal, there's various things you can change on it to encode information. So people will be familiar with like FM and AM radio. In FM radio, um, people when kind of there's to encode sound in the data, it will move the frequency up and down, and in amplitude modulation radio, when there's to encode kind of audio data, the amplitude will move up and down. So those are fairly good for encoding analog data. So like just talking into it or something. But then for encoding digital data, you can use the phase as well, which is a kind of an interesting property where you can shift a signal slightly forward and slightly back in order to kind of to make two different detectable symbols in the data, because it's all about transmitting bits in the end. And yeah, there's OQPSK, which stands for Offset Quadrature Phase Shift Keying. So, which sounds quite intimidating, but basically, phase shift keying just means that to encode a symbol, you just shift the phase that encodes a number of bits in that signal, and then you shift it back and forth and back and forth. So it's kind of like you're pressing a key for a 1 or a 0, and then that transmits a slightly different signal. Yeah, so on to GNU Radio, which was the tool I used for this, and I'm gonna have to speed up a bit, but it's basically a signal processing environment. It lets you develop and prototype various different kind of radio applications on an SDR. And it also supports a lot of kind of computational and mathematical bits that would let you do something like detecting errors and correcting errors in a signal. So it's really invaluable for what I was trying to do. So SDRs and analog to digital converters. So essentially, you can't store signals on a computer. It's an analog waveform, you know. So when something's just happening in air, you're kind of, it's moving back and forth at kind of to infinite precision. And as much as you want to store that in ones and zeros, you can't. But you can do something pretty close to that, and it's called sampling. So yeah, radio frequency waves are not digital. They are continuous electromagnetic waves. And much like with audio, you can do a trick where you just take a bunch of samples at a much faster rate than the frequencies in what you're trying to sample, and you can create a digital representation. So you might hear people complain that kind of record players and stuff are a lot better and more faithful to the original than anything you'd have in an MP3 and various things, because they actually encode kind of the analog data on the surface of the disk. They are wrong. It is just as good if you sample fast enough and you have enough bit depth. There's some maths which basically sums it up that they're basically the same, and there's nothing that you can't do in the digital domain provided you have enough storage space. Once the signal has been captured, you can then do what we call digital signal processing. So that's just a bunch of really fun maths, a lot of trigonometry, and just some really clever stuff that people have come up with for dealing for transforming signals. And a lot of it is actually very similar across RF and audio and things like that. So yeah, so that's how you get the analog into the digital domain. SDRs do a lot more clever things around that, but it's that's how that bit works. And the kind of the final technical bit, which I was gonna, well, penultimate technical bit, which I was going to talk about, was OQPSK. So it uses 4 different phase shifts to to encode kind of the bits, the things you want to send. So you can see the nice animation I have on the left, where at the top the bits which you want to send are there, and then it selects the phase from those bits and then transmits that. You can see that where the kind of different colored sections meet, you're going to have quite big jumps between that, and that can cause some issues. But that's also how on the other end it would be detected that you were sending that data at that point. Yeah. So this is a flow graph I developed. There were quite a lot of steps to uncover, and it's a fairly advanced modulation method. So I really won't go into too much detail on that. But basically, you have kind of the sampled signal. You do some filtering. You try and synchronize with the symbol, which is where basically you want to make sure that you are sampling in the correct place in order to retrieve where a kind of a 1 or a 0 has been transmitted. And then there's quite a nice thing in data afterwards called a sync word, where they inject basically a known piece of binary data for you to find to make sure that you've received that packet without any errors or with very few errors. So that's how you know that you've got a lock on the signal. And then into some of the software bits, so that I've set up as well. YAM, so it's a mission control software. You can send telecommands to your ground station, which will then be transmitted to a satellite. Receive, process, store telemetry. You can get some very fancy graphs and things. You can also do like alerting if your battery threshold is low or you're not getting enough solar power, something like that. So it's what you'd imagine all those people in the room, NASA, whatever, they're in mission control. This is the software that helps you manage mission control. It's quite a new one on the block, and is, from what I've seen, quite a lot better than some of the ones currently used by various agencies. It's open source as well, so we're free to change components of it and improve it. So it definitely fits nicely into the open source satellite project. And its kind of network and web-based nature means that you can have mission control really anywhere. It doesn't need to be near ground stations. You can just run it over the internet, which is very useful as well. And I know a lot of things are moving that way, especially when you might be using many ground stations around the Earth to facilitate your communication with your satellite. You can just have, say, a VPN set up to those places, and YAMS will just work. Yeah, so I decided to package that software onto the Raspberry Pi using Docker. So it's a Linux-based application container system, so it makes it very easy to reproduce once I've kind of written the recipe for how it's done. It means that people won't need to do too much work to move it between things, and also it means I don't have to develop it on, like, configure everything on the Pi and write a lot of instructions. I can just make a fairly simple file on a computer, share that with other people, and they can build it on whatever platform they want. So it helps it stay within kind of the versatility of kind of a ground station, because people can be doing really, really whatever. And yeah, so very easy installation and also quite good networking capabilities. So it lets you set up and specify where you want things like the web application to be, and makes the life of kind of sysadmins and things a lot easier as well. gPredict, so this is a software that we use for I've selected to use in this project for tracking satellites across their orbit. So it supports TLEs, the things I talked about earlier, so it can download those from an online source like NORAD or Celestrak or somewhere, and then it will be tracking satellites through their passes. It will tell you what the elevation is going to be, when the pass is going to start, when it's going to stop, and it also knows exactly where you've got to be pointing, which is very useful because you can then tell it to control your rotator, point your satellite dish at something, and you can set it up so just when you click on one of the satellites on the screen, it will just move it into position and then track it across the satellite's path. It also calculates all the Doppler information, which is very useful, and it will pass that on to is capable of passing that on to a kind of a radio or modem, so that you don't have to manually adjust the frequency as the satellite's passing over. So it supports some of the rig CTLD, which is like for controlling a radio, so it will be setting the frequency for Doppler, and ROT CTLD is for connecting to rotators. So here I have some information on rig CTLD and ROT CTLD. So basically, the TLDR of that is that they'll connect to a whole bunch of different systems. And it works with kind of my prototyping GNU radio as well. But I kind of need to wrap this up. So for the future, what I've still got to do is do quite a bit of documentation for some of the things already done, and for the YAML config, I'll document as I go for that, because I need to make sure that people are able to recreate exactly the software setup that I have on the Raspberry Pi, which will be in the instructions for the ground station. I'll probably do some kind of a blog post on the demodulator I've done, because I couldn't find anything else online, so I'm sure it will help other people trying to do similar things. And the constructing and programming of a azimuth and elevation rotator, that's probably one of the biggest things, and how that goes depends on what we get with the ground station gear when that comes in. So hopefully I'll be doing something with that, but if not, I'd probably do some kind of model, and potentially do a bit of research on what things there are that people could communicate with that they're allowed to, obviously, which means you're not allowed to transmit to many things without a license. I know radio amateurs they have a lot of satellites in orbit, so that can be quite an interesting topic, but for open source satellites, mainly focusing on kind of the mission control TT&C side, and then publish my source code. But thanks everyone for listening.
Next up, we have Harvey and his project, STM32 Onboard Computer Arduino Integrated Development Environment.
As a little introduction to my SPIN10 I'm looking at using an STM32 chip on making sure that we can use it within Arduino's integrated development environment. So basically, we want to create some kind of documentation and some actual files and some profiles for certain boards that we can use in the Arduino IDE. And there's a few different variants of a certain type of chip, which makes stuff very easy because you can just build upon one chip, kind of change it out. So the reason you actually want to use the Arduino IDE is it does just make it a little bit easier to program these chips. It just makes it easier to see the code. It's all in one place, and it's not as confusing as potentially some other environments. And again, so just by doing this, it helps speed up testing, development, prototyping, just to keep everything a bit easy, and then you can just get it done. When it comes to actual kind of flight software or testing, that will be handled by different programs that go into a lot more detail. But in terms of just on the desk, you want to do a proof of concept, it's a really good tool. So just to kind of reduce all of that to the main objectives is to create a custom board manager for the boards that we want and to the needs that we want to use the boards for. And we want this manager to create the code, compile it, and upload it to the chip. So it just handles it for us. Don't want to have to keep using different files, going between programs. We want it to just be a click of a button. And also write some example code and libraries that introduces you to using some of the terms in Arduino, or have some nice libraries and some code that can do some complicated stuff for you in just a few lines, which just helps with testing. So overall, my actual plan broken down with the project is kind of split up into the weeks. I have missed a little bit, so I'd like to say I'm kind of in week 3 of the work. So again, like James, for the first kind of week or 2, it was more just a bit of research, understanding how do you actually do this, because it's very easy to use, but it's quite complicated to kind of create yourself from scratch. And then just reviewing that chip, like I said before, that's on quite a few boards, and kind of understanding what it can do, why do we want to use it. And then going forward from now is kind of tailoring the board manager to the actual chips and actual boards that we've got to make use of the stuff that we actually want to make use of. And again, it's just to build upon that, to make it for the actual boards, do some testing, and then hopefully finally create a nice kind of polished package that we can push out at the end of it and maintain over a long period of time. To kind of take a step back is to think about what actually are microcontrollers, which this project is centered around. So they're really low level, almost stupid computers in terms of you can tell them what to do exactly. They don't do anything fancy like your normal computer with graphics and stuff, or at least at the lower end. They kind of just can do on and off, and they can do some nice communication stuff. And again, it's kind of split into the CPU, where it does all of these calculations. It can tell it what to do. It has some steps to follow. And then it also has some memory on board where it stores the code that you want it to do. It can store some values, some variables, kind of other useful things that you actually want to keep doing. And then what is Arduino? So Arduino's an open source company that make it easy to get into the world of microcontrollers, electronics, and stuff like that. So they offer a nice program where you can code and talk to these chips. But they also have their own boards with some of these chips on that make it very easy to use and kind of play around with. And again, they support a wide range of microcontrollers and chips, so you're not kind of limited. However, they don't support all of the chips, which is kind of what I'll get into in a bit. So they actually sell some of the boards. It's very easy to get involved with. It's really easy to kind of start with the basics, learn how to code, but also with doing so, these chips are kind of not best performance. They're kind of at the cheaper end, but that's what you kind of expect when you're getting into it. You don't really need to be doing loads of fancy things. But when you do want to move on to the fancy things, one of the main brands you kind of want to go to is ST Microelectronics. So they have a kind of brand or branch called STM32, which is their powerful kind of microcontrollers, especially the ones that we're using. It's a very high-end performance one. So these are kind of like industry standard. Obviously in space they're made a little bit different, but they are kind of fundamentally the same. And you get a lot more options with them. The only problem is that that's a lot more things to code. It's a lot more things to control, and you get real down into the nitty gritty, which not everybody wants to do. So we want to make use of the easiness of using the Arduino IDE, but getting the full functionality and performance from the STM chips. So how does the Arduino actually talk to this STM chip? Because like I said before, Arduino, you just click a button, it uploads it to its nice ones, but how is it going to change or be different for these STM ones? So you have a thing called a core, which is files and configurations on how Arduino takes its code that you've written on the screen, converts it into some different files that it can upload to the microcontroller, and that can understand. It can take the English you've written on the screen and turn it into zeros and ones, and it's able to actually control and do stuff. So each kind of model and variation of chip is different. So a different core is required for each different kind of chip, different manufacturers, different layups, but you can also package a lot of them in one place, which is what we're doing here, just to make it easy. And again, what we're doing is we're taking the current core that STM have made to be able to use an Arduino, but we're going to kind of strip it down, repurpose it, change it around just for the KISS boards. And again, their stuff's open source. We are allowed to use it. We just want to make it nice and simple for what we want it to do. And again, they have nice kind of examples on how to play around with what they've got and add your stuff, which takes a lot of trial and error, unfortunately. Again, the actual board manager itself is a combination of that core and lots of other kind of files that can help you code or upload to the different chips you want, or you can set them up in different ways. It allows you to be able to have multiple chips within the same board manager, like I said, with all the different cores, and it keeps it all in one place, and it's able to talk to loads of different things, and it can just do it nice and easy. The only problem is, even though you code and upload in Arduino, you still need to have their uploader software in the background. And that's just because just the way that you talk to the ST chips, and you need some external hardware to plug in and code them, which is a little bit annoying. But if you already have them, and if you're already looking to work with STM chips, the Arduino is a very nice first step, whereas you would like to progress onto this kind of more in-depth software and hardware. So kind of a breakdown of what is actually in this boards manager, which is just a bunch of files, quite frankly. So this next bit is going to be a lot of red boxes and just trying to explain stuff. But the kind of main fundamental parts is you have a file called boards.txt, which is just a text file that lists all the boards that are going to be in your board manager. And again, this is where you set them up to link the configuration files. You let the computer or the core know what is the name of your board, what different files do you have to use to get that board to work, and it just piles stuff in different ways. You've also got your platform.txt, which for STM chips and the way they've done it, they've included a lot of compilers and automated kind of code in the background, and this helps link it all together and to get stuff done for you, which saves a lot of time. And your variant, which is where you include the actual different types of boards and kind of the different configurations, the different pins, the different names of all the different boards, and that's where kind of the nitty-gritty, deep down bits are stored about your board. And then to kind of have all of this get picked up by Arduino, you need to create a special file called a JSON file, which in that contains all the correct paths on how to install stuff, set stuff up. It's just how it basically is able to install board manager for you in the first place. So to break it down a little bit more, the boards.txt handles all the names and configurations, and this is where you can add all the different names. If you can see at the picture at the bottom, how it kind of branches out, that's where you add the different types of boards. So it's very useful for places like KISS where you want to have loads of different types of variations or different boards just all together, and makes it easy to kind of separate and spread it out. You could have it in a massive long list if you really wanted to, but I've split it up so you can have nuclear boards for testing. For OSAT, you can have it talk to the STM chip, as you can see right at the bottom. This is the board part number. If there were two different types of chips, you could also then change between them there. It just helps keep it all together and a bit neat, because a big long list of files, nobody really wants to read through it. And again, here's the platform.txt. So if you notice at the top bit, I've highlighted the version. This needs to be kept the same for linking it throughout different files within the core. If you mess that up, it's not going to know how to talk to it, and it's kind of a bit annoying. But as you can see as well, when you actually see it in Arduino, this is the version that pops up. So you can have multiple different versions, and depending on the version you've got, which is declared in this, kind of tells it how to set itself up. As of now, I've just put 0.01 because it's still in the test phase, but hopefully when it's ready to release, it'll be 1.0 and change with each little update we've got, which is quite nice. Luckily, I don't have to go and write these from scratch. These are supplied by STM, but they are the drivers and the bootloaders that tell STM and the program behind the scenes how to actually talk and upload the code, which very grateful they do it for me, because this is an area I don't really want to get involved in unless you have to. So this really handles the memory addresses, just stuff that is going to take too long to learn in 4 weeks. And again, so the variants, this is where you have kind of all the configuration files for each type of variant that you have. So for the OSAT, you can see on the right there, you have to you have the variant and the name with some header files and some C++ files. And this is where you declare all the certain type of pins and all the certain things specific to your variant. And then you've also got some like configuration files, some scripts, and some stuff that they handle for you to automate all the stuff in the background, which again, you kind of have to get right here, and it helps compile and run the code in the background. But again, it takes a lot of trial and error of getting stuff right to figure out that's what they actually wanted. So again, so in the C++ file, it is just a massive long list of all the pins, which is just a pain to have to write. But luckily, for the Nucleo, it was supplied. So you can see just the list of every little pin, and there's 144 pins on the STM chip we're using. So it is a very long process, which I'll have to do for the OSAT and double check and go through that every pin is correct, because you don't really want to be turning on and off certain pins. But this one taken is for the Nucleo, so it works. I don't have to play around with it. And this is also where you may have seen in Arduino where you can use certain phrases, or you can use certain commands, like the built-in LED. You actually have to link that to something, and so that's where you can do it here. And so when, like on OSAT, there's 3 LEDs, you may want to call them LED 1, LED 2, LED 3 for ease, but here is where you assign them behind the scenes. But once you do it once, you don't have to do it again, which is very nice. And again, so by following the STM32 core, which is the STM supported one, to add variants, you kind of have to play around with some stuff. So you need to generate some files to tell you all the stuff about the STM chips. And by doing that, you kind of need to change a few of the stuff so that the files can play around with it and build what they want to do. But it's very nicely documented. So in the future, if you were to add extra boards, this is the process you would follow. And again, just need to do it once, but it just gets set up from the beginning. And this is the kind of the linking script that lets you know all the memory addresses, stuff we don't have to handle with, but it's nice and important to get right at the beginning. And then this is something I discovered today as well. You need your clock file correct. So when you go between different boards, they may have different crystals or different frequencies that they need set and tuned for that certain board. And this, again, you have to get it right, otherwise no code will run, which took me about a week to realize, fortunately. And again, this you can get generated from STM's programmer, but you then need to copy and paste and put it back into this. So for when you're trying to do it yourself, you do kind of have to go out of the Arduino, go to the other IDEs, and then come back. But again, once you've done it once and on one computer, it should work for the rest of them. But that being said, when I move to the proper OSAT boards, I will need to double check and generate the correct clock configuration files, because depending on the peripherals you use, it can actually change some of the values on that. So if you want to use I2C or USB, it can actually change this clock file. So what you need to do is you need to set up the correct format of your chip in STM, copy and paste that, so you know everything should work when expected. And then again, this is something not really well documented, but something again I had to find out the hard way, is they have an automated file thing, CMake, and in that there's a file called forwards_db, and within that you then have to declare all of the specific names for your board. And as you can see highlighted in blue, it says if defined and the name of an Arduino thing. That gets declared in this CMake file. And it's very important to have that, otherwise nothing will work, because it won't know where to link your board to the other files and stuff like that. You can add it yourself and change the name, but luckily they have support for the H7 chip that we're looking towards, so I can keep it simple, not have to play too much. But things like the STM32H7XX, it says there, that is a certain keyword that is used to help compile the code and send it to the correct drives and stuff. And again, I was missing an X on that, and it took me like a whole day to realize, and it's really infuriating because it doesn't tell you, but it's something that once you get right, you then know to kind of keep track of and do it for the next. So then to basically have Arduino find this file and know exactly what to do, you have to do a file called a JSON file, which is kept outside of the folder, but it's kind of all together, so it's okay. Within that is where you set the name of the kind of the board manager, the packages, all the tools and stuff that you have behind the scenes. And again, you need to make sure that the version number is correct, as was in the platform TXT file. If these two don't line up, then nothing will work. You also need to host this file globally and open so that Arduino can talk to it. So this is hosted on a GitHub account, and Arduino is able to access the link and get hold of this. So all of these projects have to be open source, basically, which again is in line with stuff that the OS that's getting used for. Yes, but you kind of have to. Yes. And within that, you compress your core in the board manager file, and Arduino can take that and it unpacks it and does stuff like that. And again, this took a very long time. Well, actually, it was quite quick, but it's quite annoying. In Glue, you have a checksum massive string. So basically, when you download files, the computer wants to check that everything's in order. It wants to check that it has downloaded it fully. And so this massive string, it will recalculate when it downloads it, and they need to match. So that means every single time you make a change to this file and you recompress it and you re-upload it, you then need to recalculate the exact encryption key or the hash key and the exact file size, which is a real pain. So every time you want to change something, you have to then do a procedure through the terminal to be able to get the exact size, create a certain key, and then once you've zipped it and compressed it, then you change the JSON, and then you have to upload it, which is a real pain. But then also what you need to do is, once you've uploaded it to GitHub, you need to wait for the actual back end of it to update, which can take about 5 minutes sometimes, which is really slow and a little bit infuriating because you can't. It updates on the main page, but if you click and see the raw versions, it's called, it's not updated, and it's the checksum that's the important part. So you really need to wait up to update. So I've spent a lot of my time just waiting around, quite frankly, refreshing the page until it's updated and I can run everything again. And again, what you need to do is you get that link and you put it within Arduino, and that gives it the correct pathway to download everything that you want and unpacks it all and stores it within your Arduino files on your computer so it can talk to everything nicely. And this is not for most other chips, it's mainly just for STM. So you have these things called packages, and so it uses tools and some automated things that again unpackages everything, puts everything in the right place, and also uses these tools when you're compiling the code. Now, these are hosted by other people, not us or STM. However, you can download them locally, which is nice, kind of as an insurance. But what you do is it gives a link to find and download these zip files from these different tools, which is quite a pain to get wrong. So luckily, just copy and paste it and change the package name KISP so it fits all in the same place. And again, all the file names are correct. But so every time that there will be a update for one of these things, potentially you'll need to then include the newer version, update this, which is quite tedious, but it's the way it works for STM, unfortunately. That's just the way that they set it up. For other chips, you don't even need to include all these packages. So it is just kind of annoying for using STM and then being so complicated. But overall, from my actual project and what I've kind of understood so far and what I'm happy with is actually understanding how to do all of this stuff in the background. I had no clue about this before I started, and now I kind of understand what's going on with the different configuration files, the text files and everything like that. And to actually have it work, and I've compiled and uploaded code to Blinking LED to see it actually work from something you've kind of got dropped in the deep end is a really nice thing. Right. and not really creating, but more like maintaining and updating the files needed to have a board manager work is really nice. And to actually see it visualized when it popped up for the first time within the Arduino IDE saying KISS was quite a cool thing to see, because it's something that, as somebody who's used Arduino a lot, you see before, but to actually create something yourself that pops up is actually really nice. And to make sure that you kind of had all the configuration files the right way. And one extra bit, which got very lucky to understand it quite quickly, was the hash file codes for the JSON file, because on all the tutorials, nowhere actually explained what it was, and I had no clue. So I actually had to kind of half piece it together and figure out, and it was quite a nice moment when that actually came together and was like, okay, we're onto something here. And again, just to kind of reiterate it again, the activities was creating and customizing the JSON file to include everything we want, to have it here in Arduino, and to have the correct structure that I wanted, to kind of nest the different types of the boards in one place, and to put extra work in to make sure that it looks nice and is usable, rather than just bare minimum and just chucking it all together. So that's something, again, as somebody that uses projects, I want it to be easy. So I want to put the work in to make sure that this is no different. And so here is some Arduino code, just to blink an LED. And at the bottom shows that it was uploaded to the Nucleo using the custom board manager that blinked the LED. And today I was able to get it blinking using a different kind of configuration, or it was thinking it was just the generic chip, which is kind of a step in the right direction. And that again was able to blink the LED, and that issue was down to that clock file. So it's just getting down to the nitty gritty and checking, figuring stuff out, and making sure I understand what's actually going on. So just again, at the end of it, kind of stuff that I've enjoyed learning is having to actually read other people's work, especially when it's not necessarily well documented, trying to figure out what they've done. Now, the STM example is quite different, because it's like a professional organization and they are really good at programming. So it's quite hard to kind of figure out what they're doing. Again, don't fully understand everything that's gone on. However, I've managed to piece together and get the stuff working as expected. So I'm happy with that level. And also, like, learning about the behind the scenes of Arduino is something I've never delved into before, and I'm really happy I've had the chance to do it, because it's something that, although it's not as fun as programming an actual board, it's kind of what's needed to understand how everything works together. And then also reading like data sheets and documentation on the Nucleo board, CSTM chips, and assembling a JSON file is really nice as well. Just getting that all to work. And then some actual use cases for the work I've been doing is, again, to just kind of save time, allows for less experienced people to kind of just get in and program. Again, Arduino is very nice and simple to get the basics. That's how I learned. So it does just teach you the basics, but you don't have to go onto all these complicated programs and do all the memory addresses and stuff like that. That just sounds scary, quite frankly. And again, just allows for quick learning, quick prototyping, and this is kind of aimed towards a selling point for like schools and the OSAT boards, but it kind of allows for hands-on experience with kind of what real spacecraft use, but without the price tag and the complicated programming that goes on. You can just simulate an LED, or you can talk to some sensors, or you can do some low-level stuff that will replicate what's being done, just not to the same kind of rigorous standards that actual systems need to go into space. And so the next kind of part of this project, and also like past my project, is to keep maintaining this board manager. So when the core gets updated, which it actually did about 2 days ago, annoyingly, but when that gets updated, you can then just include their updates, and you can push and you can keep the core the same, just with our variants and the different boards still attached. And it should hopefully all work with minimal changing. You just kind of need to update the versions and those tools we said before. So I've started working on the custom board profile for the OSAT. As I said, I've got something working today, but again, just need to keep working on it. Create some examples for this kind of stuff that board is being used for. Again, got to double check those 144 pins, make sure they're all correct. Hopefully have a variant of version to test with and have some code on, but I know that they're kind of quite difficult to get hold of. And again, just writing, testing, get some code working on it. So you're actually able to use it and not just have some board manager that I think works. I actually want to test and improve that it does. And then also keep updating my project summary as I go. So this will definitely help me. But yeah, thank you.